All right, I'm done messing about, so you're going to get one video for all four of these problems, number 5 through 6. So you can just put me on fast forward as you are wont to do. So we've got a cylindrical tin can with a top and a bottom. So let's go ahead and draw ourselves a cylinder. Our cylinder has some height and some radius. Okay. All right. And it's 16 pi cubic inches. That cubic is signaling to us that we're talking about a volume. The volume equation for a tin that's cylindrical is the area of the base, pi r squared, times the height. And we're told that's equal to 16 pi. Let's keep reading. If a minimum amount, right there we've got something we need to pay attention to. We're minimizing whatever is about to come. All right. Amount of tin is used to construct the can, so we're minimizing the amount of tin. What is the height in inches? Okay, so we're looking for h. H is a big old question mark. Well, let me write this over here. So if we're thinking about the tin that is required to wrap around the cylinder and do that top and bottom, we're thinking about surface area. So we're minimizing surface area here. The surface area of a cylinder, well, that's equal to the circumference times the height. So 2 pi rh plus the area of the two bases plus 2 pi r squared. All right. So we're looking to minimize. So this is 1, right? And 2. We're looking to minimize our surface area. So that makes the second equation here my primary. And my constraint is the volume that I want. So the volume is my secondary equation. I'm looking to just have h in this equation because I'm trying to find h, right? So I want my primary equation to just have h in it. So in order to do that, I have to substitute in for r using my constraint equation. So I've got here my volume is equal to pi r squared h, which is equal to 16 pi. We're trying to solve for r, so we can substitute that into our surface equation to only have h's in that surface area equation. So that means I have to divide by pi r squared. Well, pi divided by pi, those guys get out of town, right? The r squareds get out of town, so I've got h equals 16 divided by r squared. And look at me saying the right thing and doing the wrong thing. So we're trying to solve for r here. Yikes. All right. So we should be dividing by pi h. So I've got r squared then equals 16 divided by, the pi's cancel still, the h cancels, divided by h. Then I have to do the square root of both sides. This would be plus or minus, but we're thinking about a height here, so we're only interested in the positive version. So I've now got r is equal to the square root of 16 over the square root of h. Square root of 16 is 4 divided by square root h. All right, so let's go ahead and substitute that into my primary equation. So I've got surface area is equal to 2 pi r. So instead of r, I'm going to have 4 over root h. Times our height plus 2 times the base area, which was pi, and then r squared, 4 over square root h squared. All right. So this is going to be easier for us to think about if I rewrite the square root h with a fractional exponent. Because we know when we have, well, let's keep going. I'll be quiet for now. We've got 4 squared and square root h squared, so that's going to be 16 divided by h. All right, so let's carry on here, as we shall. I'm going to have 2 times 4, so I've got 8 pi h divided by h to the 1/2. When we're dividing exponents, that's the same as doing the difference. So it's like h to the first. So this is the same as saying 8 pi h to the 1 minus 1/2, or 8 pi to the 1/2, h to the 1/2. All right, and then the other one, we've got 2 times 16, 32 pi over h. And we can bring that guy upstairs with a negative exponent. This is h to the first, so 32 pi h to the negative 1. All right, and now we can take a breath because we're finally somewhere that we like. All right, so our surface area equals this guy. All right. So we've now got one variable here, which is good. That was our third step, I do believe. And then we're looking to think about what values make sense. So h has to be positive, obviously, right? And it has to be less than our, well, let's just leave it at h has to be positive. All right, 5. Why do I feel like I'm messing up the numbering here? All right, so now we look at the derivative of our surface area equation. So the derivative of 8 pi h to the 1/2 would be 1/2 times 8 pi h to the 1/2 minus 1. And then we've got plus negative 1 times 32 pi h to the negative 1 minus 1. So 4 pi h to the negative 1/2 plus, whoops, minus 32 pi h to the negative 2. Let's rewrite these. All right, and we're setting that equal to 0. So this is the derivative of our surface area equation. All right, we are personally on a warpath. We are anti-denominator. We don't like those. So we can get rid of those. Whoops, this should be a positive half. We can get rid of those by multiplying through by our least common denominator. Our least common denominator here is h squared. So if I multiply by h squared and by h squared, I'm going to have 0 on my right hand side. These h squareds cancel, so I've got 32 pi. And then h squared and a half h becomes h to the 3/2 because we subtract those exponents, and we've got 4 pi. We're solving for this, so add 32 pi to both sides. Yikes. All right. All right, divide both sides by 4 pi. So those guys get out of town. Pi gets out of town. We have h to the 3/2 equals 32 divided by 4, which is 8. All right. So we want to get rid of that 3/2 exponent. So to do that, we're going to use the reciprocal 2/3, right? Because 2 times 3, well, 6 over 6, which is 1, right? So 8 to the 2/3 is the same as saying the cube root of 8 squared. Cube root of 8 is 2. 2 squared is 4. So we've got h equals 4. We need to prove that that is a minimum. So we're going to go ahead and do our number line, and we're looking at the derivative of SA here. We've got h equals 4 as our point in the middle. All right, we're going to choose points on either side and substitute those in. All right, I'm going to choose 1 on my left side here. So I'm going to have 4 pi divided by the square root, or 1 to the 1/2. All right, plus, minus 32 pi divided by 1 squared. And that's going to give us 4 pi minus 32 pi, all right, or negative 28 pi. So this is negative. So now on the other side, we're looking for a positive. We'll be happy if it comes out to a positive. I'm going to do 4. Nope, not 4. I'll do 16 on that side, just because it's a perfect square. So when I do that square root the first term, it's going to come out pretty. You, of course, could be a slacker and use a calculator, but Mr. Donahue here has had his Wheaties this morning, so he's going to go ahead and stop talking about himself in the third person, because that's weird. All right, so we've got 4 pi divided by the square root of 4 is 4, and then minus 32 pi divided by the squared version of 16 is 256. All right, and 32 goes into 256 8 times, so I've got pi minus 1 over 8 pi, which is 7/8 pi. All right, that comes out to a nice, pretty positive. So we know we have a min here. So we are satisfied with our minimum. We have to look and see what were our units. Come on. Inches. So 4 inches is our answer. Woo woo. Moving on. All right. A rancher. We're back to the rancher. He has 200 feet of fencing to enclose 2 rectangular adjacent corrals. So we've got rectangular corrals, which means fields, and they're adjacent to each other. So if they're rectangular, they've got different dimensions, right? So let's call this one X and this one Y. So we've got another Y here, another X, another X. All right, so we're looking for the enclosed area to be at its maximum. So let's write down what our constraints are here. We've got the total amount of fencing is 200. And if we were to add up all of these different pieces, we'd have 4y plus 3x equal to 200. All right. Cool. What are the dimensions that maximize the area? So we're looking to maximize the area. And area here would be equal to, all right, we've got x times y is one of the rectangles, so 2x times y. We've got our total fencing, which is constant. That's our constraint, so that's our secondary equation. We've got our area, which is what we're maximizing. So that's going to be our primary equation. So we have to substitute into our primary equation using our secondary equation, so we only have one variable. I'm going to choose to solve my secondary equation for y. So I've got 4y equals plus 3x equals 200. 4y equals 200 minus 3x. Divide everything by 4. So we've got y equals negative 3/4 x plus 50. Now we're going to substitute that into our equation for y. So I've got my primary equation, a equals 2xy. So now I've got a equals 2 times x times negative 3/4 x plus 50. When we like not expand but distribute that, we'll have negative 6/4 x squared plus 100 x. Negative 6/4 reduces to negative 3/2. All right, let me just pause for a second here and make sure that's correct. Yeah, we're all good. We're all good. All right, we need to think about numbers that make sense for our x and y. So both of them need to be positive. Right. Let's go ahead and do our optimization part, which requires us to set our derivative of the area equal to 0. So my derivative is going to have 2 times negative 3/2 x, and then the 100 just 100x becomes 100. So the 2's cancel. I've got negative 3x plus 100 as my derivative area is equal to 0. Solve for x. We get 100/3. All right, that's about 33.3 repeating. So now we just need to prove that we have maximized the area, and then we need to find the other dimension. So we've got x equals 100 divided by 3. Right. Pick a value on either side. So I'm going to pick 1 and 40. So negative 3 times 1 plus 100 is 97. So we've got positive, and then negative 3 times 40 plus 100, negative 120 plus 100, negative 20, so negative. So if we go from increasing to decreasing, we've got a max here. All right. So we've got x equals 100 over 3. Let's go back over to our original part here. So our max x is 100 divided by 3 feet. And now let's find y. So we've got 4y plus 3 times x, 100 divided by 3 equals 200. So 4y plus 100 equals 200. So we've got 4y equals 100. Y equals 25 feet. So our dimensions are 25 and 100 divided by 3. All right. Well, if we're going to be technical, that's just the dimensions for one of these boxes, right? So the dimensions for the whole thing would be 2y. So 2y is the whole area. So we've actually got 50 feet. So we're 50 by 100 over 3 feet for our enclosed area. All right, on to the next one. We're now down to 2. So we're looking at another area problem with a rectangle enclosed by the equation. I'm just going to write that here. Y equals square root, 25 minus x squared. All right, so we have a rectangle bound by the x-axis. The graph is the semicircle defined by y equals the square root of 25 minus x squared. All right. What is the length and width of the rectangle that maximizes the area? So we're looking to maximize the area. So we know we need to find some equation for the area. All right. So if we're looking at y being equal to this, that's going to be my vertical here. All right, we can call that our width if we want. And then we need an equation for this bottom piece, or length. Well, if we're thinking about how far this piece is, that's x. So the whole piece is 2x. So if I've got my area equal to length times width, and I don't mean length times width, we've got 2x times the square root of 25 minus x squared. All right, this one's gonna be a little messy, folks. All right, so let's rewrite this as 2x times 25 minus x squared to the 1/2. We can't distribute that 2x because we have that square root there. Right, but we do have an equation that already has one independent variable, so we're ready to go to the maximizing step. However, we have two pieces here, an f and a g. So we're going to need to use the product rule. And then once we get to the derivative of g, you're going to notice we have to use a different rule. So we've got f equals 2x. The derivative of f is 2. That one was fairly straightforward. G is equal to 25 minus x squared to the 1/2. Well, yikes, right? We've got an inside-outside happening here, so we have to use chain. All right, and chain said that if we've got some outside function, so in this case, to the 1/2, and some inside function, 25 minus x squared, when we do the derivative of the inside, we're going to get negative 2x. When we do the derivative of the outside, with the inside staying the same, we'll get 1 over 2 g to the 1/2. All right. So this then, we have to multiply these two results. So I've got negative 2x over, and then this is going to be 2. G we know was our inside at 25 minus x squared, so I've got 25 minus x squared to the 1/2. The 2's cancel, so I've got negative x over 25 minus x squared to the 1/2. All right, pretty gross, right? Pretty gross. So our derivative here, once we've used the chain rule, is that baby. I don't know why I just said that. I even cringed a little. All right, so let's apply our product rule, which says, I'll switch colors because why not? F prime g plus f g prime. So here we've got 2 times g and then f times g prime. We're about to do some math magic here, and you might not like it, so sorry. But it's going to make everything prettier for us to look at. Remember, this is our derivative that we're finding here of area. Okay, so still talking about our derivative of area. I've got 2 times 25 minus x squared to the 1/2. That part stays the same. And then we've got minus 2x over 25 minus x squared to the 1/2 equals 0. All right, we do not at all like that denominator. To get rid of it, we're going to have to multiply through by that denominator. So by that hot mess downstairs, we're going to multiply everything by it. So we're going to have 25 minus x squared to the 1/2 twice here. You'll notice that the inside's there. This one cancels, and that's 0. Right? You notice that the insides are the same, so we can use our exponent rule to add the exponents, since the guts are the same. I told you weren't going to like this. It's just some tricky algebra, which is kind of baloney. So this is going to be to the first. Oh, look at that. We can distribute things. Oh, fancy, fancy. So I've got negative 2x squared minus 2x plus 25. Let's see if I'm not mistaken. That should be pretty. Oh, so pretty. Okay, let's think about this. We've got negative 2 and 1, and 2 and negative 1. 1, 25, negative 1, negative 25, 5 and 5, negative 5, negative 5. Alright, we're looking for it to add to negative 2. So, let's see if any of these pairs give us what we want. 1 and 5 and negative 2 and 5. Oh, and look at Donahue making mistakes here. This should be 50. That changes these a bit. All right, so and we've got something that's unfactorable. Lovely. All right, let's take out the greatest common factor. All right, and then we'll use the quadratic formula once we get rid of that negative 2. So opposite of 1 plus or minus the square root 1 squared minus 4 times 1 times 25 over. Oh, this is flips to a negative. You pull out a negative too. So we've got negative. And then divided by 2 times a, so 2 times 1. Negative 1 plus or minus square root of 1 plus 100 over 2. And if we put that in a calculator, we are going to be interested in the positive version, and we will get about 4.525. So this was hecka gross, not gonna lie to you. Alright, so we're gonna have to do our a prime on either side of that. 4. What did I say? 525. Alright. These were all a prime going down, right? So I'm going to choose the one that is the easiest to substitute into, to use. Right, and the easiest one to substitute into is right here. So I'm going to use 1, and I'll use 10. So I've got 2 times 25 minus 1 squared minus 2 times 1. So I've got 25 minus 1, which is 24, times 2 is 48, minus 2, 46. Positive. Alright, and then we'll use, well, 5, why not 5? Alright, so we got 2 times 0, minus 10, negative 10, so we're negative, and we've got a max, so x equals this, is a max, which we were looking for a max, so we're all set. That problem was like hard. Alright, similar problem, let's hope we're prettier. Alright, so we've got our y here is our height once again, and that's negative 4x squared plus 4x. And similarly, x is halfway, right? So overall is 2x. All right, we're looking for the x and y coordinates for the point C so that the area of the rectangle is at its max. So we've got A, our area, equals x times y, which is x times negative 4x squared plus 4x, which is negative 4x cubed, 2x here. All right. Negative 8x cubed plus 8x squared. All right, we need x and y to be positive. So those are the numbers that make sense. Let's go ahead and do the derivative. 8 times 3, negative 24, x squared plus 16x equal to 0. Greatest common factor, we'll take out 8x. That leaves us with negative 3x squared. Negative 3x plus 2. All right, so we've got two solutions here. We've got when 8x equals 0 and when negative 3x plus 2 equals 0. All right, 3x equals 2, x equals 3/2. All right, so 0 doesn't make sense. 3/2, well, that makes sense. So we've got the x coordinate here because we just said x is 3/2, right? We need to make sure that's a maximum, and once we've done that, we can find the value of y. All right, so we've got x equals 3/2, and we're looking at our derivative area equation, which is that negative 24 x squared plus 16x. All right, I'm going to use 2 and 1. So I've got negative 24 times 1 squared plus 16 times 1. Negative 24 plus 16, which is negative 8. Ugh. Guys, I'm so sorry. There's a mistake that followed me all the way through this problem. Ugh. This was just plus 4. So this should be plus 8x. I copied that equation down wrong. I'm so sorry. It's going to change everything. Changes everything. Oh, I hate this. Why did I have to do that? So we've got plus or minus square root of 1/3. The only one that makes sense, because it's a positive x coordinate, is the square root of 1/3, the positive version. So I'm so sorry I made that mistake. Ugh, it's the worst. I guess we all make mistakes. Ugh, so upset. All right, so let's pick a value on either side. So we can use 1 still. And that gives us -16, so we're negative on this side. And then a value that's smaller than square root of 1/3. So square root 1/3 is about 0.57. So we can use a half. So -24 times a half squared would be 1/4 plus 8. So -24 divided by 4 is -6 plus 8 would be 2. So we're positive. So we've got a max when x equals square root 1/3. So our x coordinate, square root 1/3. So now we need our y. So y equals -4x squared plus 4. Plug in your x, so -4 times square root 1/3 squared plus 4. -4 times the squared and the square root cancel, 1/3 plus 4. So -4/3 plus 4. We need this over 3. -4/3 plus 12/3. 8/3. So our point is square root 1/3 comma 8/3. Sorry I made that mistake, guys. Ugh, it's gonna haunt me now.